I also thank Ashish Gupta, who initially proposed that I should give this talk. So I'm very much pleased to participate in this RKMV Ramakrishna Mission Vivekananda Educational and Research Institute. So the idea of this seminar is to talk mainly about two topological theorems, so the Brouwer's fixed point theorem and the Bourgeois-Coulomb theorem. So, and then illustrate some combinatorial connections. So Brouwer's fixed point theorem, I have been talking about it for a long time. I think right in the beginning when I started my research career, I was interested in the constructive proof of Brouwer's fixed point theorem, which came about in the mid or late 60s by some economists, especially Professor Herbert Scarf. And he gave a constructive proof which was very much of interest for finding equilibrium points in economy. And the idea of the constructive proof was quite different from the traditional combinatorial algorithms where you have some objective function and you improve that function every step. But here there is no objective function. And so it was quite a different type of approach. And I will say a few words about that. And then I have been talking about Brouwer's fixed point theorem, about Squareless lemma throughout. And in fact, so that is not my sort of main area, but I keep on doing something, and I'll present one or two small results which I proved many years ago, not as the main point of this talk. But my very first paper was some kind of combinatorial generalization of Brouwer's fixed point theorem that appeared in Journal of Combinatorial Theory, Series A, which is now a very prestigious journal. Even at that time it was, but somehow I sent my manuscript to Professor Kifan, and he liked it, and so that is how it started. And later on, I have kept in touch, and surprisingly, there have been recent developments. They keep on coming related to Brouwer's fixed point theorem and Squareless lemma. So I want to present some very fresh, relatively very fresh results. So the Brouwer's fixed point theorem part, obviously the whole talk is very elementary, but I want to convey something which is attractive and new perhaps to some of you. So that is the idea. It doesn't get from the mathematical point of view, perhaps you may not find very, perhaps not deep, but they are highly applicable and relevant in some areas. Okay, so initially I'll start with some notation, the usual notation. So we have this disk and sphere. So disk means the closed sphere or sphere with the interior. So we have this norm x, Euclidean norm, and the Bn is the ball in Rn. So x belonging to Rn, norm x less than or equal to 1. And Sn minus 1 is the boundary of Bn. So I illustrate this with some pictures. So here is S1 is the interval minus 1 to 1, and sorry, B1. And S1 just S0 rather consists of the 2 points minus 1 and 1. So this case is not very interesting for us. So the next case is B2, which is the ball in R2, and its boundary is S1. And then one more case, and B3 is the sphere in R3, and S2 is its boundary. So for almost throughout the talk, I'll restrict myself to 2 or 3 dimensions. Many of the statements are true in higher dimensions, but the proofs and ideas are similar, so I may not present them that way. And also, I may not be interested in the ball for the Brouwer's fixed point theorem. Rather, I would be interested in the simplex, the triangle, and the two are equivalent, so it doesn't matter really from the point of view of result. So this is the statement. Here I have stated it for Bn. So if you have a function from Bn to Bn which is continuous, then there exists x naught such that it is a fixed point. So f of x naught is equal to x naught. And so as I said, later on I use the simplex instead of Bn. So here the only assumption and the main assumption is continuity. And if you violate continuity, then obviously the theorem breaks down. For example, you can have a map from say B2 to B2, where all the points are mapped to the origin, and the origin is mapped to somewhere else. then that doesn't have a fixed point. But obviously, it is not continuous. So it's very easy to see why continuity is important. But interestingly, that is a very weak assumption. That is the only assumption that we need. And I won't go into the usual proofs of Brouwer's fixed point theorem. Several proofs are there, but I'll indicate one of the proofs which uses Squareless lemma. So not completely, but give you an idea. Okay, so there are equivalent versions, and to illustrate Brouwer's theorem in small dimensions, if you take the function from 0, 1 to 0, 1, which is continuous, then it has a fixed point. And this is a consequence of the intermediate value theorem, because here you see the black graph is the graph of the function, and this is the red line is the line fx equal to x or gx equal to x, and it cuts the line somewhere, and so there is a fixed point. Of course, sometimes people conjecture that there are an odd number of fixed points. So parity plays a role. In the combinatorial setting, the parity very much plays a role, as we will see. But at present, we cannot make any such statement. And the proof of this particular version is quite elementary. So, but the higher versions, you require some technique for Brouwer's fixed point theorem. Okay, so there are some equivalent versions, quite a few equivalent versions. So one of them is the no retraction theorem. So no retraction theorem says that you cannot have a map from Bn to Sn minus 1, so Bn to its boundary, such that on the boundary it is the identity map. And this is the no retraction. You cannot have a retraction of the sphere onto its boundary. And it's not surprising, because if you want to continuously map Bn to the boundary, then some tearing has to be done. You have to tear apart somewhere. Without that, it cannot be done. And that will spoil continuity. Now, why are the two equivalent? So, first of all, the no retraction theorem implies Brouwer. That's quite simple, but let me just say why. So suppose you have a function f from it to the ball to itself, which is continuous, and suppose it does not have a fixed point. Then you take fx, take x, and since they are not equal, the line segment is well defined, and you extend the line segment to hit the boundary at gx, and then you clearly get a continuous map G, which is a retraction, because on the boundary it is going to be the identity map. Because if x is on the boundary, then gx will be equal to x. So if there is no fixed point, we have got a contradiction. And so no retraction theorem implies Brouwer's fixed point theorem. The reverse is actually quite simple, but I have found that if you ask it to graduate students, they are not immediately able to answer. So why does Brouwer's theorem imply no retraction theorem? There's a small trick actually. Trick means something that students usually miss. You can try this. So suppose you have a retraction. Then you just take the retraction and compose it with a rotation. Then it will not have a fixed point, and then that violates Brouwer's fixed point theorem. It's very simple. So if Brouwer's theorem holds, then there cannot be a retraction. So the two are equivalent. Okay, some more versions. So here is the main combinatorial version, Squareless lemma, which I like very much. Eugene Squarler has two lemmas to his credit, but somehow the other lemma, which is about binomial subsets of a set, that is more famous among combinatorialists. Squarler's lemma, which I am presenting, is also well known, but perhaps not that well known. But now it is getting popular due to some applications. So you have a, now I'll come back to a simplex. So by the simplex, I just mean this triangle, and you have a triangulation. So I will not go into the general definition of a triangulation. You can have, need not have a regular triangulation like this. It can be any subdivision into simplices, such that the intersection of two simplices is either a empty or a subsimplex. So that's more general, but for our purpose, it is enough to consider this grid kind of thing. Okay, so you take the simplex and take a triangulation, and then you label it. So the labeling has to have some properties that the corners get the labels 1, 2, and 3. Here I have 1, 2, and 3. And on the edge 1, 2, you can have 1 or 2, but not 3. Similarly, here you can have not on the edge 1, 3, you can have 1 and 3. Otherwise, there is no further condition. And on the edge 2 and 3, you can have anything other than 1. And inside, there is no condition. You can have 1, 2, or 3. So this is called Squarner labeling. And the Squarner lemma says that if you do a Squarner labeling of this triangulation, then there is one subsimplex. So by simplex, subsimplex, I just mean one of these triangles, which is completely labeled. That means it carries all the 3 labels. So here I have given some random, forget about the plus and minus for a moment, but I have given some random integers 2, 3 in the interior. And now you can see for yourself that there are several simplices labeled 1, 2, and 3. So there has to be at least one. But there is more to it. So here is where the degree theory comes into play. And if you assign a plus and minus sign to these simplices, like for example, this simplex is positive because its orientation matches with the main orientation. This is anti-clockwise. And so I label it plus. Whereas this is also a completely labeled simplex, but this is also a plus. And this one is labeled minus. And so the number of pluses exceeds the number of minuses by exactly 1. So that is the degree theoretic or oriented version. Actually, the Squarner's lemma in the one lower dimension, just for a line segment, is even easier. That if you break a line segment into small segments and label it 1, 2 on the endpoints, and inside 1 and 2, then the 1, 2 labeled will be number will be odd. It's even easier. This particular version requires a proof, and so I was interested in. I will not indicate a proof now, but I'll give some idea of a existence. That means how to find this completely labeled simplex, because ultimately we are going to use it for some numerical procedure. So you will have a very big triangle, very big simplex partitioned into very small subsimplices, and then your interest is to locate that completely labeled simplex. So you require some constructive procedure, and this is what initially there was a very short one-page paper by Cohen, who gave an idea, and later on Scarf developed it into a full monograph, and that has been highly used in numerical methods in finding fixed points. So if you search fixed point calculations, you will find lots of books and papers, and the area was very active in the 60s and 70s. Okay, so I think I'll indicate some, just an idea of how this constructive proof comes about. So you basically enter the simplex. So take 1, 2, for example, here is the segment 1, 2. So you think of that as an entry point. So you enter the simplex through that. And if this had been 3, then you are done right away. But here it is not 3, then you definitely have one more edge, which is 1, 2. And you sort of, that tells you where to go. So you proceed there. And now you have found a 1, 2, 3. This is a very small example, so we terminated very quickly. But what can happen? What can happen is that, so it can be proved combinatorially. The proof argument is not very difficult, that this algorithm will not cycle anytime. And the worst thing that can happen is that you may enter through, like I think perhaps I can illustrate it here. You enter through this 1, 2, suppose. Now I haven't found a completely labeled simplex, but I have found another 1, 2. So I proceed, and then I have found 1. But had it been a 2 here, then I would proceed and sort of come out. And now I use this odd number. So I know that the number of completely labeled simplices is odd, even at the lower dimension. So I can re-enter. So that is basically the idea. And there are versions of this algorithm to speed it up, and many numerical procedures or numerical simplifications have been found. And in fact, this last point here, so I'm giving here some applications of Squarner's lemma. In the 90s, late 90s, this algorithm became very popular among computer scientists. I'm not familiar with those developments, but I roughly know what's going on. that they use it as a standard model for some computational complexity. That is, they are interested in what is the computational complexity of this method and how efficient this method is, and so on. So, although it was developed in the 60s, it has had a resurgence in terms of research interest. Okay, some other applications. So, one application is constructive proof of Brouwer's fixed-point theorem, and this fair division problem and rent sharing. I think Professor Ajit Iqbal Singh sent a mail and listing a lot of papers. And these things are very interesting, by the way. I mean, one can sort of give a undergraduate colloquium on any one of these problems because they are not trivial. There's interesting applications for Squareless lemma. And so these are some of the main applications. And I'm sure there are others. And I want to later on present one somewhat recent application or recent version of Squareless lemma. So now proceeding to other equivalent results for Brouwer's fixed point. This is the Canister Graph waves lemma. You take the simplex and cover it with three closed sets, C1, C2, C3, such that this vertex is contained in C1, this is in C2, this is in C3. This edge is in C1 union C2. I have written it down. So T is the triangle, usual triangle. C1, C2, C3 are closed sets such that the endpoints Vi belongs to Ci. C1 contains the edge V1, V2, etc. And the union contains the whole triangle. Then the conclusion is that their intersection is non-empty. And this is sort of, again, equivalent to Brouwer's fixed-point theorem. And one can work out, or even as an exercise, that is a one-way implication. You can construct a suitable labeling, which is a Squarner labeling, and apply KKM lemma, and so on. I will not say more than this. But there are several such results about the intersection being non-empty. Okay, so I have written.
Sir, there are any applications to linear algebra also?
Yeah, linear algebra. My favorite application is coming up. It is the Perron Provenance theorem. So I'll make some remarks. Next, it is right here. So Perron Provenance theorem again has several proofs, and one of them, which is very interesting, at least that proves the basic part of the main part, that if you have a function, if you have a matrix, and which is non-negative or positive, then you construct this function fx equal to, yeah, my pen. Okay, so fx equal to ax divided by, here non means just the sum of the coordinates. So A is a positive matrix for the time being. Non-negative is also okay sometimes with some conditions. Okay, so A is a positive matrix. X is a probability vector. So non-negative with some 1. Then if you consider this map, Ax divided by the sum of the coordinates, then this maps the probability vectors to probability vectors continuously. So it has a fixed point by Brouwer's theorem. And once you write down the fixed point equation, you will immediately get the eigenvalue eigenvector equation. So it has a positive eigenvector and a positive eigenvector. The main assertion of Perron Provenance is immediately proved by Brouwer's fixed point theorem. And one more interesting application is the minimax theorem of von Neumann of game theory. And that was proved by Kakutani fixed point theorem. But Kakutani fixed point theorem is essentially an extension of Brouwer's to set maps, set valued maps. But it can also be done by Brouwer's fixed point theorem. You can say minimax theorem is also a theorem in linear algebra. It's a theorem about linear inequalities. And interestingly, here Brouwer's fixed point theorem is actually stronger than minimax theorem. Actually, my advisor spent many years in the beginning to prove the reverse implication. He very much believed that Professor Raghavan, he believed that minimax theorem can also imply Brouwer's fixed point theorem, but he could not succeed. And I can see now it is clear that Brouwer's fixed point theorem, although it is elementary, it's a non-linear theorem. I mean, there is no linearity in the assumptions. And so anything non-linear will require taking a very strong theorem in linear algebra. You cannot prove Brouwer's fixed point. One can try. That will be interesting. Okay, so no retraction theorem. I am not aware of any other application. Fixed point theorem applications in linear algebra generally go like this. construct a map. And okay, then I have talked about Squareless lemma and then the RKMVERI lemma. Kroneker's theorem is very much about maps with non-zero degree. So, but the degree 1, so Brouwer's theorem is essentially about degree 1. And Kroneker's theorem says that if you have a map from the ball to itself, such that on the boundary it preserves the boundary and has degree 1. For example, the identity map. Then the map is onto. That is Kroneker's theorem. And more generally, if you have, of course, continuity has to be there. If you have a continuous map from the boundary to the from the ball to itself, such that on the boundary it preserves the boundary and has a non-zero degree, then also it is on. Okay, this hex game is not equivalent. This is a mistake, but hex game is very much related to. I will not go into the description, but it is very much related to fixed point theorem, although it is not. Okay, so Squareless lemma, why does it imply Brouwer's fixed point theorem? So take a map from the triangle to itself, and you devise. So then I have to show that it has a fixed point. You devise a labeling scheme, and it will turn out you first triangulate the triangle, and then you devise a labeling
But
scheme.
what did you mean by degree? Can you go back to the last one?
Yeah. Degree is the, I think the topology students may be familiar with the binding number or the topological degree.
Oh,
means,
okay, fine.
I think graduate students will be familiar, so I did not go into that. The usual topological degree. If you have a map from S1 to S1, then you take the inverse image of any point and count the points plus minus.
Okay. No, I understand it.
Yeah. Okay. Okay, so Squareless lemma, why does it imply Brouwer's fixed point theorem? So take a map from the triangle to itself, and then the labeling scheme is quite interesting, or that does the trick. So label the vertex like this. Take any label in the triangulation, and if v is equal to f of v, we are done. That's a fixed point. Otherwise, because both are probability vectors in the simplex, so some vi has to exceed some f of vi, ith coordinate. Then you label it with I. If there are two such I, then you choose any one. So that is the labeling scheme. And you can see that this satisfies the Squareless condition. Like just to go back, no matter where f takes this point, definitely 1 is going to exceed the first coordinate. So this will definitely get the label 1. This will get the label 2. This will get the label 3. Similarly here, no matter where it goes, it will get the label 1 or 2. So ultimately, by Squareless lemma, there will be a triangle which is completely labeled. So imagine this triangle is completely labeled. Then in this vertex, the first coordinate exceeds the first coordinate of the image. Here the second, here the third. So you can imagine that by going to the limit, if this is very small, then anything here will be an approximate fixed point. So ultimately, you have to use a limiting value. I'm not going into details, but it's quite straightforward. So this is how Squareless lemma implies Brouwer's fixed point theorem. And here the converse is also true. That means Brouwer's theorem also implies Squareless lemma. So I think I was going to talk about one or two results which I do long back. And this was inspired by a multi-function version. Actually, David Gale, a very famous economist, had a multi-label version of Squareless lemma. So what he said is that you label each vertex with 3 labels, 1, 2, 3. Conditions are here it should be 1, 1, 1, here it should be 2, 2, 2, etc. Here 3 should be absent, and so on, the usual conditions. And then his conclusion was that there is a simplex such that if you take the 3 labels here, 3 labels here, 3 labels here, actually you will get a matrix. And in that matrix, you can always find a diagonal, a permutation, such that the sigma 1th element in the first row, sigma 2th element in the second row, and sigma 3th element in the third row, they are distinct. So it's sort of a refined version. And when all the 3 labels are identical, you are back to Squareless lemma. So I just converted into continuous functions. I had some other results, but one of the results was that a multi-function version of Brouwer's fixed point theorem. That if you have 3 functions from triangle to triangle which are continuous, then there exists a point x and a permutation sigma such that the ith coordinate of x is greater than or equal to the sigma ith coordinate of x. So this implies usual Brouwer's theorem, because when all the functions are the same, then you will have x equal to f of x, because then you will have xi greater than or equal to f of I x, but both are probability vectors, so they have to coincide. So I think this multifunction idea can be used for other theorems also, although I have not explored that. And but it's a sort of the way to extend. And there are some advantages. You can do some more refined degree theory and so on. Okay, one more version of Squareless lemma, or rather related to Squareless lemma, which I want to talk about. This is a recent result. Recent means 2005-6, and this was used in again an interesting problem in combinatorial for the bandwidth of a graph. I will not go into that, but certain bandwidth could be found, and the result is very interesting. So consider a triangulation, and now you color each vertex red or blue. There are only two labels, and interesting thing is there is no condition. There is absolutely no condition. I have to define what is called a connector. So connector means like this vertex here is a connector, because this vertex is a red vertex, and from there you can go to this side only using red vertex. You can go to this side using only red vertex, and you can also come down to this side using only red vertices along the path. Such a thing is called a connector. And the theorem says that if you label each vertex red or blue, then there is either a red connector or a blue connector, but not both. Actually, not both is easy to see, because so in this example I have a red connector, which I just showed. But once there is a red connector, it kind of constructs these barriers, and so there is no way you can have a blue connector. So that part is okay. The first part, interestingly, is proved using Squareless lemma. So I think I'll just tell you how is the labeling, and you can try it later on. It becomes just an exercise. That you take a vertex, and suppose you can reach from that all the sides, like this is blue. Suppose you can reach this side, you can reach this side, but not this side. Then you label it, this side is labeled 2, then you give it the label 2. That means whichever side is not reachable, you give that label. And if there are two sides, you choose the smaller one. So I think I'm going a bit fast here, but later on see the labeling, it will turn out this is a Squareless labeling, because from this vertex you already are sitting on these two sides. So the only side you cannot reach is the bottom. So that way it satisfies the Squareless labeling, and for the Squareless triangle, and then one small argument. So I will not say much more.
Professor Bapat, I mean, can I interrupt?
Yeah, sure.
Does the proof yield some estimate on the number of these same color dots on a connector?
Yeah, actually that is done a little bit in the graph theory application. So yes, there is some estimate in that. Yes, I would say yes, and some connection. Actually, if you Google, I have a paper on this, which is refers to the original paper. But the original paper, I don't have the author's name and all that. But if you Google bandwidth of a triangulated triangle, then you will get all this paper. The first paper, bandwidth of a triangulated triangle, and there is an estimate which uses to find the bandwidth. That was an unsolved problem for some time.
Okay. I mean, we have sharp upper bounds right now.
Yeah, but yeah, there are bounds. I mean, I don't know whether there are straightforward bounds, but your question to your answer is just there's something about the number of these connected. Okay, so I had one more version which was again inspired by, because this lemma does not imply Squareless. Squareless lemma implies this result, but not conversely. So I wanted to sort of remove that drawback. So here is one thing I again wrote long time back, that you label these vertices with integers, any number of integers. No, you can use natural numbers. No condition, absolutely no condition. So you use any number of labels. Then the conclusion is the following: either there is a simplex with distinct labels, or there is a number k which is a connector. So one of these, here both things can also happen. But either there is a simplex with distinct labels, or there is a number k which is a connector. And this will now imply Squareless lemma also. I will not talk about that. Okay, so I think with that I will proceed to the other Borja-Coulomb theorem. The Borja-Coulomb theorem and Brouwer's theorem sort of Borja-Coulomb theorem, like elder brother of Brouwer's fixed point, are very stronger and along similar lines. Okay, so I have to talk about antipodal maps and so on. So antipodal, so a function on Sn is called antipodal. First of all, antipodal map function is called antipodal if it maps f of minus x is equal to minus f of x for all x. And the identity map is an example of an antipodal map. Okay, so Borja-Coulomb theorem, there are a couple of versions. So I have not stated some, I omitted some versions, but only 4 versions. So what is the basic version? You have a map from Sn to Rn. So think like S1 to R1. It is continuous. Then there is a pair, by the way, these points are called antipodal, x and minus x. So there is a pair of antipodal points, x naught and minus x, that where the map coincides. F of x naught is equal to f of minus x. And as you can see, for a one dimension, again, it is just the intermediate value theorem essentially, because you can have, like if you have a map from S1 to R1, then you can, so F is a map, then you go to the map G, which is fx minus f of minus x, and as you can see, it will have, fx minus f of minus x, and now you can, if you take any point, then on that point and the antipodal point, the map will have opposite signs. Actually, they are negatives of each other. So and the map is continuous. So in between, it will attain 0, and that means f satisfies that condition. So it is again very easy. So in the lower dimension, and in the higher dimension, one picturesque way of remembering it is that at any given point, there are 2 antipodal points on the Earth's surface where both the temperature and the pressure coincide. Consider the temperature as a continuous map and pressure as a continuous map. Then you have a map from the Earth's surface to 2 dimensions, and by Borja-Coulomb theorem, there are 2 antipodal points where they coincide. Okay, that is the basic version. Another version is there is no continuous mapping from Bn to Sn minus 1 to the boundary, which is antipodal on the boundary. That is f of minus x is equal to minus f of. And as we will see, this is clear. It immediately implies Brouwer's fixed point. One of the equivalent versions of Brouwer's fixed point. Okay, the next version, if you take a cover f1, f2, fn plus 1 of Sn by n plus 1 closed sets. So they need not be disjoint, their union just contains Sn. Then there is at least one set which contains a pair of antipodal points. And the previous version is true if each fi is either open or closed. So these are the 2 versions which I'll refer to this in the application. And there are a couple of more versions which I'll give reference to that. Okay, so here is one illustration with S1. If S1 is covered, so I'm illustrating the 3rd version. If you have a cover n plus 1, f1, fn plus 1 of Sn by n plus 1 closed. Okay, so I have a cover of S1 by 2 closed sets. Then one of them will contain, at least one of them will contain a pair of antipodal points. So here the blue, I mean these are covers, so I have not colored it inside, but sets, covers. So this contains a pair of antipodal points. Okay, that is the illustration of this. And Borja-Coulomb implies no retraction, because if you go back to the 2nd version, that there is no continuous map from Bn to Sn minus 1, that is antipodal on the boundary. So if there is a retraction, remember the definition of retraction, then a retraction is a map which is identity on the boundary. So clearly that is antipodal. And so that violates the 2nd version of Borja-Coulomb theorem. So no retraction theorem is an immediate consequence of V2. and so no retraction is equivalent to the hour 600. So Borja-Coulomb theorem is clearly stronger. And of course, I don't think the converse will be true. Okay, now about the proof of Borja-Coulomb theorem, many of them are topological, and I have not really followed because I have not done this in a course or taught a course. But there is a combinatorial analog, and perhaps that's the only route I know to Borja-Coulomb, and that is called Tucker's lemma. So Tucker's lemma talks about a triangulation of Bn. So here I have considered B2, and you triangulate it, and on the boundary, the triangulation should respect antipodal point. That means if this point is there, a vertex, then the antipodal point should also be a vertex. Inside there is no condition; it's just a triangulation. And then it's the labeling. Labeling is with 1 and 2, and in general it will be 1, 2 up to n. But labeling here is with 1 and 2, and here also there is a condition that antipodal points should get opposite labels. So this point has got a label 1, so this point should get a label minus, and so on. So this point has got a label 2, so this point is minus. So throughout the boundary, it should respect this antipodal points having opposite labels. Inside there is no condition. And what is the conclusion of Tucker's lemma? Tucker's lemma's conclusion is very weak in a sense. It just says that there will be, no matter how you label it, so inside I have not put any labels, but no matter how you put the labels, there will be one line segment, not a simplex, but a line segment. And this is true even in higher dimensions. That there is a line segment which carries labels 1 and minus 1 or 2 and minus 1. So I have written it here, that there exists an edge whose endpoints carry both labels 1 and minus 1 or 2 and minus 2. So higher dimensional analog I am not stating precisely, because it takes some time. But why this implies Borja-Coulomb is also not that straightforward, but is again you have to go to a finer and finer triangulation and then apply a limiting argument. But it will be an interesting exercise to see the proof. But Tucker's lemma is the combinatorial analog of Borja-Coulomb. Okay, now I'll go to the main application that I had in mind of Borja-Coulomb theorem. So I'll talk about chromatic number of a graph, but for the final problem, this chromatic graph theory is not required. But anyway, just to set up the stage. So as you know, you have a graph, and then you can color the vertices with some colors. And the vertex coloring is called proper if adjacent vertices get distinct colors. And chromatic number of a graph is the minimum number of colors required for the proper coloring. That is, like the planar graph has chromatic number 4 and so on, at most 4. Okay, so here we are going to consider this very special graph called a Canister graph. And this is denoted by KGN, so there is a parameter n. The vertex set is the set of all 2 subsets of 1 to up to n. So there are n choose 2 vertices. And 2 vertices, so you take a vertex ij and a vertex kl. They are said to be adjacent if their intersection is empty. So ij and kl are adjacent if their intersection is disjoint. So this is called Canister graph. And this has been well studied in set theoretic combinatorics, very well known graph. And one small example is that if you take the Canister graph on 1, 2, 3, 4, 5, then you get 10 subsets. And if you make the graph out of it, that turns out to be the well-known Peterson graph. And as you can see, the Peterson graph has chromatic number 3, which I have illustrated here. So you can color Peterson graph with 3 colors, such that, and 3 is the minimum, that any 2 adjacent vertices have different color. So the conjecture, there was a well-known conjecture which was open for a long time, that 1955, that the chromatic number of KGN is n minus 2. So it is illustrated by the Peterson graph, 5 minus 2. The chromatic number is 3. So it was conjectured by Canister that chromatic number gave a proof in 1973. And that essentially led to the development of topological combinatorial. So proving topological theorems by combinatorial techniques. And the proof was later on simplified, Parani and Green. Okay, so now it is really a set theory problem. So I'll illustrate an example which will make clear the complete technique. So we will take KG10, so Canister graph on 10 vertices, and show that the chromatic number is 8. General idea is similar. So it's a set theory problem. What is the problem? You consider, so I'm not talking of graphs. In the between, I may talk of a graph also, but as I said, graph theory is not essential here. So you take 45 pairs of integers, 10 choose 2, and you color, you say that 2 are adjacent if they are disjoint, as in the graph context. So I want to partition the 45 pairs into k sets such that in each set no two pairs are disjoint. That means that will determine the coloring. So k colors will be sufficient because in any partition, if no two are disjoint, that means they are not adjacent, because if they are disjoint, they are adjacent. So no two are disjoint means in each partition they are not adjacent, and so it is a coloring. So what is the minimum value of k? And we want to show that the minimum is 8. So there are two things to be shown, that 8 is actually 8 works and 7 does not work. So that is the thing we have to show. So the fact that 8 works is somewhat by construction, as always. So you take the two subsets and partition them as follows. A1 consists of the pairs 1, 2, 1, 3 up to 110. A2 consists of the pairs 2, 3, 2, 4 up to 210, dot, dot, dot. A7 consists of 7, 8, 7, 9, 7, 10. And A8 is a small twist that I can take 8, 9, 8, 10, and I can also put 9, 10 along with it, because there also any two will not be disjoint. I don't have to construct A9. So if I color all the pairs in A1 with one color, all the pairs in A2 with one color, and so on, second color, and that way I color with 8 colors, then it will be a proper coloring. And so definitely chromatic number is less than or equal to 8. And once 8 is enough, then 9, 10, 11, they will also be enough. So the main thing to show is 7 is not sufficient. Which means we have to show that if you partition the two subsets of 1 to up to 10 into 7 sets, try to be ambitious and have a coloring, then you will not succeed. That means one of the AIs definitely will contain a pair of disjoint sets. That means in the Canister graph will be adjacent and your coloring will fail. So no matter how you partition the 7 subsets into, the 45 subsets into 7 sets, no matter how you do it, one of them will contain a pair of adjacent vertices. Okay, so here is where the brilliant topological idea comes into play. So I think up till now, nobody even thinks that, let alone Borja-Coulomb, but any topology is going to give this. I don't think one can imagine, but this is how the area has started. Okay, so here is the idea. You place the 10 points, not the pairs, but the 10 points on A7. A7 is the sphere in general position. General position just means that no 8 of the points are of the same grade 6. This is like our non-degenerate condition. Very often we talk about points in the plane, no 3 on a straight line, something like that. This can be done by small perturbation, not a strong condition. So put them in S7 such that no 8 are on the grades, same grades here. Okay, now here's an important definition. For any point P in S7, let HP be the open hemisphere centered at P. So it is a kind of a cap which is centered at P. So just to illustrate, that means suppose you have the sphere, and I'm taking the sphere in ball in 3 dimensions. And if you take a point P, then you construct a cap which is centered at P. So the picture is going to be complicated, but something like this. You take the cap, so this cap, an open cap. You take the open cap centered at P. And you do that for each and every point. So for P, let HP be the open hemisphere centered at P. This definition is very important. Now I define some sets. So for I equal to 1 to that, I define the cover and then apply Borja-Coulomb. So for I equal to 1 to up to 7, let ui be the set of all points such that the cap that we just constructed contains a pair of points in AI. So U1, for example, U1 is the set of all P such that the cap centered at P contains a pair of points in A1. Similarly, U2. U2 is the set of all P such that the open hemisphere centered at P contains 2 points in A2, etc., all the way up to U7. They are not disjoint or anything, this is just a definition. And to make a cover, I just take the complement and put everything in U8. So I get a cover. As I said, they are not disjoint, but I get a cover. And here, U1 up to U7 are open sets, and U8 is a closed set. But that is okay in the Borja-Boulogne, one of those versions. So each UI is open and U8 is closed. So by version 4, there exists a UI containing a pair of antipodal. So what does that mean? So suppose U1 contains a pair of antipodal points. So let's say I have to use UI, but let's say P belongs to U1 and minus P also belongs to U1. That means HP and H minus P both contain a pair of points. That means a 2 subset contained in A1. But then they have to be disjoint because one cap and the other cap have nothing in common. They are open. And so this shows that they have to be disjoint. And so the result is proved in this case that 2 subsets they must clearly be disjoint. And so the result is proved. So let me repeat. Suppose you have a point in U2, a P point, and a point minus P also in U2. Then H of P and H of minus P will both contain pair of points in A2, and then the result is true. Okay, so I hope that this point has been appreciated. It takes some amount of introspection, but maybe you can think about it. Okay, now one case that remains is that U8 also cannot contain a pair of antipodal, because suppose P belongs to U8 and minus P also belongs to U8. Then by definition of U1 up to U7 and U8, H of P will contain at most one element from the original set. Because if H of P contains 2 points, then it will go to one of those UIs up to 7. I equal to 1 to up to 7. But that doesn't happen. So because P is in U8, H of P contains at most one element. Similarly, H of minus P contains at most one element. But then where are all the remaining points? Because if you consider HP complement intersection H of minus P complement, that means that should contain at least 8 points remaining. But here is where the non-degeneracy assumption is required. That is not allowed by the non-degeneracy. So that shows that in any of these cases, the result is good. And I think I'll just show the main points again. I'm just covering the same thing because this requires, until you master the argument, it is a little elusive. So this is basically the proof technique. Okay, but I think if you just go over it again, then, or maybe many of you probably have already seen it. But when I saw it for the first time, and now this area has developed into topological combinatorics, and there are many other results which are proved along similar lines. I think I'll illustrate one more, not the proof, but just the one more result. And these are called necklace splitting problems. And there are a host of such problems which are now solved by topological methods. So there are a group of problems on special divisions of sets of discrete objects. And Allen and Douglas West made some initial contribution around 1987. And a typical problem is you have a necklace with beads of different colors. And the necklace should be cut and divided among several pieces or partners such that each one receives the same number of beads of each color. And of course, the number of cuts should be minimum, otherwise you can always do. So I have illustrated it with one example. That here is a necklace, which is, there are beads. And as you can see, there are, what is important is there are an even number of red beads, namely 8, and an even number of green beads, namely 6. And so don't look at the cuts right now, but no matter how you do these beads, put them in the necklace. The necklace splitting problem, this is also basically one very simple version, by the way. You can have any number of colors and you can have different conditions, you can have different requirements on the cuts. And it's an whole area of necklace splitting problem. And the conclusion is that I can cut the necklace here and here, so that will cut it into two pieces, the top piece and the bottom piece, such that the reds and the greens are equally divided. Both are equally divided. For example, the reds are divided 4 and 4, and the greens are divided 3 and 3. And that is the conclusion. So no matter how you put the beads initially, an even number, and then you can always make these cuts so that beads are equally divided. And as I said, this can be done with more colors and so on. Okay, so I think I'm just going to give some references. So I'm not listing any research papers here, but the main references. So the standard book is Using the Borja-Coulomb Theorem by Matthew, very comprehensive book, and lists all the proofs and all the applications, many of them. But for us, Squareless lemma is not given that much importance. The Squareless lemma, I think, I have not given the complete proofs like the fair division problem and the rental agreement. And the proof was simplified by Green. And then if you see the Wikipedia pages on Borja-Coulomb theorem, topological combinatorics, and necklace splitting problem, you will get many more. Okay, so I think I'll stop with that. Thank you.
Okay, let us thank the speaker. Thank you, Professor Bapat. Any questions, comments, remarks?
I have a couple of things to ask, Sudeshna. Can I?
Absolutely.
Professor Bapat, if we have the analogous, Canister graph on vertices consisting of k subsets, do we know something about the corresponding conjecture, the analogous conjecture?
Yeah. But I have not. That means there will be some result about k subsets. But we have presented here is just the two subsets. But for k subsets, unfortunately, I don't have the answer right away. But I think one has to go to the references. And but I am sure that the set dividing sets has been considered in detective. Maybe the references.
Okay. And secondly, right? Does Brouwer imply Borja-Coulomb?
No. I believe not, because Borja-Coulomb theorem is implicitly stronger. It is a very highly integrated. Some topology is coming into play. So I believe not. So I have not seen a proof, and I believe that Borja-Coulomb theorem is strictly stronger than Brouwer's theorem. But ultimately, it may be proved in future. But I believe not. So far, no.
Well, the third is a comment, if I may indulge. These are typically finite dimensional phenomena. And one who happens to be interested in infinite dimensional structures, all these theorems fail in infinite dimensions, and in fact characterize finite dimensional spaces. For example, if you have a Banach space and you ask yourself whether Brouwer's fixed point theorem holds, the first implication is that it always fails, but once it holds in a Banach space, then it is so it's bound to be finite dimensional. So that's another aspect of it. Very interesting at that. It was just a side comment that I am personally, involved in or interested in at least.
Okay.
So I have one question, sir. What is this? Is there any application to multilinear algebra?
Multilinear algebra, you mean tensors and so on?
Yes, something like exterior powers or something like that.
No, I would say no, not directly. No. I mean, you can have a cross product. You can have multidimensional. You can have a cross product of several simplices, and then there will be fixed point theorems and so on. I don't know whether that counts as a multilinear algebra. No, not directly. Not aware.
Actually, what I had in mind was Lowash has found out some connection between exterior powers, exterior algebra, and some graphs. I think hypergraphs, some hypergraphs.
Mhm.
So, I mean, regular hypergraphs.
Mhm.
So, so this is how I thought maybe that there is also connection.
Okay. Okay. Not familiar.
I mean, just one more small thing I would like to ask Professor Bapat. We have we have elementary proofs of Bowers fixed point theorem. You know, like something that uses some important theorems from advanced calculus, like Stokes theorem. Uh, do we know of a proof from calculus or some elementary proof of the Borja column?
Borjakulam, I tried to go through this Matusek book, which gives several proofs. The only proof I could appreciate was the through Tucker's lemma, because all other proofs, which was combinatorial, and I could see it in front of my eyes. But other proofs, to me, they were all mathematical. I don't even, I'm not in a position to even describe, but they look not elementary to me. So Borjakulam theorem, I have not seen what, as you say, what I would call an element. Maybe there in the missing. I'm not sure.
Uh, so, sir, one more question, please. What is the most, I mean, student friendly, I mean, reference for this these
I think
prediction of
the
results?
book which I listed, Matusek, is quite readable. It is quite student friendly. You can use it as a graduate. You can use it as a course for senior undergraduates even. You can omit parts of it which require higher mathematics, but this is a very nice book. So I think that would be a great reference on Borjakulam.
So did you find any combinatorial application of Jordan curve theorem or higher dimension of that? You know,
Jordan
from
curve.
because
No, no, Jordan curve. Some combinatorial ideas keep coming up, but I don't know what you mean by
you don't know.
application. Like I have seen where
Because
several combinate for
that
fundamental
is
theorem of calculus. I've seen several complex polynomial having a root. I've seen constructive proofs and it has in similar spirit. Jordan curve.
because you see you have covered these important theorems in topology, Bauer's fixed point theorem and Borsuk-Ulam theorem and such. And the next in the line is
Okay.
Jordan curve theorem.
Okay.
So that is why I asked.
Okay.
So there's no combinatorics there because they also, they compute homology groups and such. Uh,
Yeah. Yeah. Yes.
so
I wouldn't say there is combinatorics, but
uh,
no right now.
okay. Because you see this Bhaskar Bakshi and such, they developed topology quite a bit combinatorially. They were all
Mhm.
giving versions of these things. So from there, a lot of, obviously it uses a lot of combinatorics,
Right. Right.
their things. So, whether it's,
Right.
so from there, did you find some analog of those kind of theorem?
No, I haven't looked enough. I think I will try.
Oh. Anyway, nice seeing you after a long time.
Yes, I am seeing you. Very happy to see you.
Yeah, and also to Sudekshna.
Yes, nice to
But I keep catching up with you, Shashi ji, once every while.
हाँ हाँ हम लोग तो एक कमिटी में हैं so there
Right.
is Aditya Kual ji also
Ji,
always
ji.
present. I mean I'm always amazed to see her whenever I see her. Oh my God, what a lady.
Yes.
Thank you, thank you. Applications to fair division and cake cutting problems also.
Yeah, that
Yes.
is standard. That is known.
Actually, Professor Iqbal, I was requesting you to give some kind of cake cutting problem talk.
No, I used to give long time ago, long time ago. Now I think new work should be exposed.
Ashish, I already requested and she didn't agree, but I hope we can keep pushing her so that she ultimately agrees.
Absolutely.
Thank you, thank you.
Okay, so let's thank the speaker one more time. And
Thank
just
you.
to let everyone know, tomorrow we have another talk, our regular colloquium. So Professor Bruno Pugi, he is from University of Barcelona. He will be giving a talk on operator theory. So
Acha,
that's
What is the
tomorrow.
topic? What is the topic, Sudeshna? Have sent.
It's I can send you the announcement if you want. It's exponential decay of solutions to Schrodinger operators with electric or magnetic potentials.
So it's not our operator theory.
Yeah, but he gave a talk at Bunyani's lecture series also, Bruno.
Okay.
Sudeshna, I keep on getting this information about your colloquium via some other person.
Well, I am not in the colloquium committee. Stefan and Shamik are the in charge, though I arrange the talks, but I am
Okay, so I will ask Samik. Stefan is away, so I will ask Samik.
right. He can put you in the list. Yes. Okay. Bye, everyone. Hope to see some of
Bye.
you at least tomorrow.
Thanks,
Bye.
Professor Bapat. Thanks,
Thank you.
Sudeshna.
Thank you. Thank you.
Thank you, Professor Bapat.
Thank you.
Oh, I have to stop recording first.
Thank you. Thank you. Wonderful.
So good to see you, Ajit ji. Now you cannot escape. Yeah, she
Okay.
also wants you to be here. You have to give a talk.
Fine. 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 Okay.
I will
Thank you.
schedule you, okay?